Because airplanes are flying high and fast, energy management is a key issue in flight mechanics. After a short revision of kinetic energy, we will see how the work done by an external force modifies this kinetic energy. We will then look at potential energy in order to define total energy and total height. The kinetic energy of a solid body in a translational motion, i.e. with no rotation, is 1/2 of its mass, m, multiplied by the square of its speed, vg. G here designates the center of mass or the center of gravity. Here, mass is expressed in kilograms, speed in meters per second, and energy in joules. The work done by a constant force R applied to a body moving from point A to point B is the product of the component of R parallel to AB by the length of this displacement. This can also be expressed by the dot product R dot AB. This work is an energy in joules that is received by the body. Now, when we sum the work done by all the external forces applying on a body, we obtain the variation of its kinetic energy along the path from A to B, which is EKB minus EKR. Let's consider now the particular case of the work done by the weight mg along a path from A to B. As the gravity is constant and vertical, we can easily show that this work is equal to mg multiplied by ha minus hb, whatever path we follow from A to B. When we climb from A to B, the work done by the weight is negative. It resists our motion, removing energy from the airplane. It is as if the energy has been removed and put in a tank. The level of this tank only depends on the height of the airplane. If the airplane descends back to height HA, it will then recover exactly the amount of energy lost during the climb. We call this tank of energy potential energy, and we note it EP. We can express it as the product mgh. We are now able to define the total energy as the sum of potential and kinetic energies. And what is really useful is that the total energy variation when the airplane is flying from A to B is just the work done by all external forces except the weight, and there aren't many such forces, typically thrust and drag. What we also see here is that without giving extra energy to the airplane, with the total energy remaining constant, we can still exchange huge quantities of energy between potential energy and kinetic energy. So, regarding energy, flying slowly at high altitude is equivalent to flying fast at low altitude. Rather than dealing with joules, it is interesting to use height to quantify the aircraft energy state. For that, we define total height. Total height, ht, is the height at which potential energy would be equal to the total energy of the present state. So, mght equals mgh, with h being the current altitude, plus 1/2 of mv2, the current kinetic energy. This gives us ht equals h plus v2 over 2g, which is not dependent on m. So total height depends on speed and altitude, that's all. It doesn't depend on mass. Total height is the altitude at which, if the pilot pulls up, the aircraft will stop and start going backward. Total height can be easily represented in a speed-altitude diagram. Here, we can see that flying at ground level at 570 knots gives us the same total height as flying at 15,000 feet at zero speed. As a practical illustration, we can consider a fighter plane flying at very low altitude at 500 knots, which is quite a high speed. Following an engine failure, the pilot can react with a quick pull-up, exchanging speed for altitude in a very short period of time. Of course, the aircraft cannot decelerate to a complete stop, but 100 knots is probably a reasonable speed. The aircraft has climbed slightly above 10,000 feet, giving plenty of margins to deal with a failure, relight the engine, or prepare to eject.